When retrofitting a plant and needing to feed a new motor control center, or MCC, from an existing one, and space is limited in the old MCC, tapping off the existing bus becomes a viable solution. The National Electrical Code, or NEC, provides guidelines for such installations, specifically concerning outside taps. The question at hand revolves around the interpretation of Section 240.20. B5 of the NEC and whether the tap location must be physically outside the building. According to the NEC, the tap location does not necessarily have to be outdoors, but it must be nearest the point of exit of the conductors from the building. This means the disconnect is not mandated to be outside, but it should be as close as practically possible to where the conductors leave the building or structure. The disconnect's location can be either exterior or interior. In the context of the scenario, the fuse disconnect can be installed in the old MCC room, provided it's situated nearest the point where the conductors exit the building. This interpretation is further clarified in the 2020 NEC commentary on Section 240.20. B5. The commentary emphasizes the proximity requirement, indicating that the disconnect should be placed as close as feasible to the point of exit. Considering the specific design involving running conduit directly through the wall of the old MCC room onto a pipe rack, and subsequently into the new building, the placement of the fuse disconnect inside the old MCC room is acceptable, as long as it's nearest to where the conduits pass through the wall. Understanding the requirements for outside taps involves several key considerations. Firstly, conductor ampacity. The conductors from the tap to the overcurrent protective device must have an ampacity that is not less than the calculated load served by the tap conductors, and not less than the rating of the overcurrent protective device at the termination of the tap conductors. Secondly, overcurrent protection. The tap conductors should be protected from overcurrent by an overcurrent protective device, the ampacity of which does not exceed that of the tap conductors. Thirdly, tap length. The length of the tap conductors is crucial. The NEC specifies different requirements based on the length of the tap. For example, Section 240.21. B1 addresses tap conductors not over 10 feet long, while Section 240.21. B2 covers tap conductors not over 25 feet long. Fourthly, enclosure requirements. The overcurrent protective device for the tap conductors must be enclosed in a suitable enclosure. This enclosure should be readily accessible and should protect the device from physical damage. Fifthly, identification. All tap conductors must be identified at their termination points to indicate their purpose. This identification helps prevent accidental disconnection or incorrect reconnection during maintenance or repairs. Sixthly, grounding. The tap conductors must be properly grounded in accordance with Article 250 of the NEC. Grounding ensures that fault currents can safely return to the source, minimizing the risk of electrical shock. Seventhly, supports. The tap conductors must be adequately supported to prevent strain on the conductors and their terminations. Support should be installed at intervals that comply with the NEC requirements. Eighthly, working space. Sufficient working space must be provided around the tap conductors and their overcurrent protective devices. This working space allows electricians to safely install, inspect, and maintain the equipment. Ninthly, accessibility. The tap conductors and their overcurrent protective devices must be readily accessible for inspection, testing, and maintenance. Obstruction should be avoided to ensure that electricians can easily reach the equipment when needed. Tenthly, coordination. The overcurrent protective devices for the tap conductors must be coordinated with the overcurrent protective devices for the feeder conductors. Coordination ensures that only the faulted circuit is interrupted, minimizing disruption to the rest of the electrical system. The main disconnect in the new MCC should be rated appropriately for the loads it serves. In this case, 600 amps main disconnect seems suitable if it matches the calculated load and provides adequate overcurrent protection. The installation of the tap conductors and the fuse disconnect must comply with all applicable requirements of the NEC, as well as any local codes or regulations. It's recommended to consult with a qualified electrical engineer or inspector to ensure that the installation meets all safety and code requirements. Considering the scenario specifics, If the tap is indeed an outside tap according to the NEC definition, the feeder conductors don't necessarily need to match the protection of the old MCC, which is rated at 1200 amps. Instead, the focus shifts to matching the rating of the new MCC main disconnect, which is 600 amps. However, it's crucial to verify that all conditions at the new end are met, including conductor ampacity, overcurrent protection, and equipment ratings. To further elaborate on the requirements for tap conductors, the NEC provides specific guidelines in section 240.21. These guidelines vary depending on the length of the tap conductors and the type of installation. For instance, section 240.21. D1 addresses tap conductors not over 10 feet long. This section specifies that the ampacity of the tap conductors must be not less than 1/10 of the rating of the overcurrent device protecting the feeder. Additionally, the tap conductors must terminate in a single circuit breaker or set of fuses that will limit the load to the ampacity of the tap conductors. On the other hand, section 240.21. D2 covers tap conductors not over 25 feet long. In this case, the ampacity of the tap conductors must be not less than 1/3 of the rating of the overcurrent device protecting the feeder. Furthermore, the tap conductors must terminate in a circuit breaker or set of fuses that will limit the load to the ampacity of the tap conductors. It's important to note that these are just two examples, and the NEC includes other specific requirements for tap conductors depending on their length and application. The choice of overcurrent protection for the tap conductors depends on several factors, including the ampacity of the conductors, the type of load being served, and the available short-circuit current. Circuit breakers and fuses are the two most common types of overcurrent protective devices used for tap conductors. Circuit breakers offer the advantage of being resettable, while fuses provide a more reliable form of overcurrent protection. The selection of the appropriate overcurrent protective device should be based on a thorough evaluation of the electrical system and the specific requirements of the installation. Furthermore, the installation of the tap conductors and the fuse disconnect must comply with all applicable requirements of the NEC, as well as any local codes or regulations. It's recommended to consult with a qualified electrical engineer or inspector to ensure that the installation meets all safety and code requirements. The layout of the conduits and the outdoor pipe rack must also comply with the NEC requirements. The conduit should be properly supported and protected from physical damage. The spacing between the conduits should be sufficient to allow for adequate ventilation and to prevent overheating. Additionally, the conduit should be installed in a manner that minimizes the risk of water ingress. The entry point of the conduits into the new building should be properly sealed to prevent the entry of moisture and pests. The conduit should be routed in a manner that avoids obstructions and provides easy access for maintenance and repairs. The installation of the conduit should be performed by qualified electricians who are familiar with the NEC requirements and local codes. In addition to the NEC requirements, there may be local codes or regulations that govern the installation of electrical equipment. It's important to check with the local authorities to ensure that the installation complies with all applicable requirements. Local codes may address issues such as permitting, inspections, and specific installation practices. Compliance with local codes is essential to ensure the safety and legality of the electrical installation. When designing the retrofit, it's crucial to consider the available short-circuit current at the tap location. The overcurrent protective devices for the tap conductors must have a sufficient interrupting rating to safely interrupt the available short-circuit current. If the available short-circuit current exceeds the interrupting rating of the overcurrent protective devices, the equipment may fail to interrupt the faults, leading to equipment damage or personal injury. A short-circuit study should be performed to determine the available short-circuit current at the tap location. The results of the short-circuit study should be used to select overcurrent protective devices with an appropriate interrupting rating. The short-circuit study should be performed by a qualified electrical engineer or technician. Grounding is another critical aspect of the electrical installation. The tap conductors must be properly grounded in accordance with Article 250 of the NEC. Grounding ensures that fault currents can safely return to the source, minimizing the risk of electrical shock. The grounding system should be designed to provide a low-impedance path for fault currents. The grounding electrode system should comply with the NEC requirements and should be properly sized for the available fault current. The grounding conductors should be securely connected to the grounding electrode system and to the equipment being grounded. Regular inspections should be performed to ensure that the grounding system is functioning properly. Furthermore, surge protection should be considered to protect sensitive electronic equipment from voltage transients. Voltage transients can be caused by lightning strikes, switching operations, or other electrical disturbances. Surge protective devices, or SPDs, can be installed to divert voltage transients away from sensitive equipment, preventing damage. The selection of SPD should be based on the voltage and current levels of the electrical system. The SPD should be installed in accordance with the manufacturer's instructions and the NEC requirements. Regular testing should be performed to ensure that the SPD are functioning properly. In summary, when retrofitting a plant and feeding a new MCC from an existing one via an outside tap, meticulous attention must be paid to the NEC requirements and local codes. The tap location doesn't have to be physically outside, but it must be nearest the point of exit of the conductors from the building. Compliance with the NEC ensures a safe and reliable electrical installation. Firstly, understanding conductor ampacity is crucial. Secondly, ensuring proper overcurrent protection is essential. Thirdly, carefully considering the tap length is necessary. Fourthly, adhering to enclosure requirements is important. Fifthly, implementing proper identification of conductors is vital. Sixthly, grounding the system correctly is paramount. Seventhly, providing adequate supports for conductors is necessary. Eighthly, ensuring sufficient working space around equipment is essential. Ninthly, maintaining accessibility for inspection and maintenance is critical. Tenthly, coordinating overcurrent protective devices is important for system safety and reliability. The specific requirements for tap conductors, as outlined in section 240.21 of the NEC, must be followed. The choice of overcurrent protection, whether circuit breakers or fuses, should be based on a thorough evaluation of the electrical system. The installation of conduits on the outdoor pipe rack must comply with the NEC requirements and local codes. The available short-circuit current at the tap location must be determined, and overcurrent protective devices with an appropriate interrupting rating must be selected. The grounding system must be designed to provide a low-impedance path for fault currents, and surge protection should be considered to protect sensitive electronic equipment. By adhering to these guidelines and consulting with qualified professionals, the retrofit can be completed safely and effectively, ensuring the long-term reliability of the electrical system. Remember to always prioritize safety and compliance with the NEC and local codes when performing any electrical work.